All right, good morning, everybody. We are going to today do a couple of different things, but I wanted to start out with a couple of announcements. The first announcement is, and you might have heard this on the news already, that today at 4:30 there is a rocket being launched. Have you heard about this? Okay, so I encourage you to watch that. That's going to be the first launch of human beings. It's a Elon Musk special going up to the space station. So we're taking people from the US up, and we haven't done that in many, many years from this country. So it's kind of exciting. It's a little nerve-wracking, but Elon Musk has had a lot of successful launches. And so we're hopeful that this will be another, transport vehicle to the space station. So that's 4:30 Eastern time, and I'm sure it'll be aired on major network TV, not just NASA TV and all of that. Another thing that I will post a link to on Google Classroom for later, I just found out about this last night, is tonight at 6:30 at West Virginia University, Duncan Lorimer, who is one of the people that is, he's actually discoverer of fast radio bursts, and also is one of the people who works with us in the Pulsar Search Collaboratory, is doing a presentation at the West Virginia University Planetarium. So I will post a link to that again at 6:30 tonight. It is a presentation to the public, so it should be very accessible. It will be also, I think, a nice review of Pulsar work, and that's helpful to you, I think. But also, he will talk about fast radio bursts and what those are, because we have not discussed those, but they are a very new, relatively new discovery in this field, and pose quite a mystery. So he will be giving updates on what people think about fast radio bursts, FRBs. Okay, so those things are so new that they're really not even in textbooks yet. So it's kind of neat to think of physics and astronomy and astrophysics as always progressing, new stuff being discovered. Okay, we don't know all that there is to know, quite obviously. All right, and then the last announcement that I want to make today is about tomorrow's class and the upcoming week. So tomorrow's class is going to be primarily going over problems from last week, the numeric parts of it that we did not go over, and then also you'll have some time, if people don't want to stick around for the rest of the class tomorrow, to kind of do additional work following on what we'll begin today. So I wanted to let you know that. And then that gives us just one more week of class and we're done. We will be having a test next Thursday. So that'll be our last thing together. Thursday afternoon, we'll take that science time at 2 o'clock or 2:15, whatever it is, to do a test. So just sort of put that on your radar, that that's coming down the pike, and that's going to be covering this unit that we have done on Pulsar. So we'll do plenty of review for that next week. All right, so today I want to share something with you, and this is a lab activity kind of for us. I'm going to share my screen and take you to a new place. This is called, actually I'll share this, called the Zooniverse. Okay, so minimize this. All right, so I am here at a place called zooniverse.org. This is the website right up here, Z-O-O, zoo. There is no U before universe, so it's the Zooniverse rather than universe. And the project that I'm looking at is called the Aurora Zoo. So later today, not right now, but later today, I'll ask you to go on, your own screen and find zooniverse.org and make yourself a Zooniverse account. It's very simple, but Zooniverse is really amazing because it'll allow you, if you're interested, to do many, many different projects. And they're not all science related, but they are all kind of crowdsourced research. So this is an opportunity for you to do some really important research in many areas. And you can kind of go down a rabbit hole and be following, all of these cool different projects, and, look up and you've noticed 5 hours have passed. But it's pretty neat. So what we're going to be doing is helping people actually doing research classifying auroras. So I already asked, and some of you said you were able to view yesterday's Block 4 class. So let's start by reviewing, first of all, what is an aurora? What is that?
know it's charged particles in the atmosphere, but I'm not sure the
Okay.
specifics.
Okay, charged particles in the atmosphere. What are the charged particles? Well, where are they coming from?
The sun.
The sun. Okay, so they're from the solar wind. So they're flowing here. And then what we see is we see this glow of light. So where's the light coming from? It's not the charged particles directly, but relate this back to what we're thinking about with pulsars and magnetic fields. Go ahead, Ben.
Doesn't it come from like the radiation, which like bumps into the charged particles, which like moves their energy level?
Okay, good. So we have these charged particles coming in and they are striking atmospheric particles, okay, atoms in our atmosphere of things like, and in that presentation yesterday, you'll see oxygen, nitrogen, other gases in our atmosphere collisionally excited that then drop down and radiate. Okay, so again, I encourage you to go back and take a look at that to get the mechanism there. And they're funneled by way of magnetic fields, just like the funneling on a neutron star, all right, pulsar, that charged particles get kind of tangled up in these magnetic fields and are driven and directed by them, all right? So that's how it's kind of related to what it is we were doing earlier. Okay, so here on the screen, you can see some information about this project. How does nature create such a beautiful show? Just what we described there, and here's a nice picture with a radio telescope. So I'm just going to read a little bit of this to you. So the University of Southampton operates a camera system called ASK, which stands for Auroral Structure and Kinetics, for studying the aurora. It has telescopes to look at just a small part of the sky in detail, so we see the smallest shapes in the auroras. Its detectors are very sensitive, so we can use short exposure times and see fast movements. ASK has been operating on Svalbard in the high Arctic since 2007 and automatically takes data whenever it's dark. We now have thousands of hours of video of aurora, most of which has never been looked at. So far, we've just done event studies where we have investigated specific auroral events in detail, but we want to be able to do statistical studies on the data. Okay, so that's what we're going to help with. All right, so the aim, two main science aims of this project are first to understand how the small scale shapes and movements in the aurora are formed, and then to learn what conditions are needed for those different shapes and movements to happen. So you may wonder, like, why is this applicable in our lives and all of that stuff? It goes on in here and describes us. But if you think about this, the one thing I asked you in the beginning was, where are these charged particles coming from? They're coming from the sun, the solar wind. So the sun is a star, which means that it has very, and it's a main sequence star, it's kind of an average star, has relatively consistent flux output, but it does vary. And so we do have storms on the sun that make their way by way of coronal mass ejections to Earth. And so we can, have geomagnetic storms arise as a result of this. So if you go to spaceweather.com, one of my favorite websites, you can look at kind of the impact of these solar storms. You can kind of predict them coming. If you see active areas on the surface of the sun, prominences detaching and so on, but there's still not 100% understanding of how what's going on the sun and what's going on inside the sun affects our weather and climate today, and if there's a direct correlation, or there's some processes that have to be in place, and if what we put into our atmosphere affects this at all. So any understanding that we can get based on auroras can be helpful to trying to put together all these pieces that govern our weather, govern our climate. So different things, just a temporary thing like our daily weather versus what's going on over a long scale time period, and also maybe even with the Earth's magnetic field. All right, so how can I contribute to the Aurora Zoo? Well, you're going to be watching video clips that ASK recorded, and you're going to diagnose the shape of the auroras. All right, so we're going to go through a little bit of a tutorial. How the aurora is formed, this figure is something like what I showed you yesterday. So if at your leisure, if you read this in terms of the about, you can get more information about the project. So here is a kind of, this is when I was in Alaska and I saw auroras. This is kind of what I remember it looking like a zigzag in the sky with a very sharp edge on one side and then kind of fuzzy above. So if you look, you can see some kind of faint green structure here, and it's very sharp down here. And maybe there's a little bit of pink or red underneath that. Okay, so that's an auroral arc over Finland. Going down, you can see other kinds of displays. We'll look at the field guide in a minute too. This is a rayed auroral arc, so that's looking a bit different than the other one. You can kind of see those spikes sticking up there. They all sort of look like they're pointing at the same spot in the sky. Look at this. See the purples in there? That's looking straight up at something called a corona. This is kind of an atypical aurora. Like this looks like a little question mark or something going on, a fiddlehead in there. It says here auroral arcs typically drift southward in the northern hemisphere across the sky before, and these are all going to be from the northern hemisphere because they're coming from Ask, before fading or moving northward again. Or if an event called a magnetospheric substorm occurs, then they can explode poleward so that the aurora fills the sky. Svalbard is so far north that on the night side of the planet, the aurora usually appears on the southern horizon first and moves northward before retreating back to the south. So it can also see aurora on the day side of the planet where arcs are often less clear. And of course, some of these places have, 24 hours of night during certain months of the year. All right, the pictures in Aurora Zoo are actually false color pictures. So when you see the aurora with your eyes, it usually looks green or red, as we've already discussed. Sometimes it has those other colors like purple and whitish because you're seeing a mix of colors. This describes once again what I told you yesterday about the heights in the atmosphere and the different gases the colors are produced from. And again, here it says the false color images that you're looking at are made in a particular way. So let me just read this before we go look at the field guide. So the Ask instrument filters out most of the aurora light to look at specific colors. By a careful choice of filters, we can use Ask to measure the energy of the precipitating electrons entering the atmosphere to produce the aurora. The color of the images in Aurora Zoo represents the energy of the auroral electrons, with yellow being low energy and blue being high energy, with green in the middle. Imagine throwing a tennis ball into water. The harder you throw it, the deeper it will go. Similarly, the more energy the precipitating auroral electrons have, the deeper down the energy reaches into the atmosphere. Okay, so remember, the electrons are coming from the sun toward the earth. So the higher energy they have, the deeper they're going to penetrate once they get caught in that magnetic field, and then they're going to crash into the atoms in our atmosphere. So one of the Ask cameras records red light from nitrogen at 673 nanometers and another infrared light at 774 nanometers. So of course your eye can't perceive that, which comes from atomic oxygen. The 777.4 nanometer light comes from higher up than the 673 nanometer light, which makes it sensitive to lower energy electrons entering the atmosphere. So by comparing the brightness of the two emissions, we can work out the energy of the auroral electrons. So they mix it down to a color that you can see in the pictures you're about to. All right, so over on the right side of your screen, once you're in Zooniverse, you will see something called the field guide. So I'm just going to click on that, and this is our teaching guide. So look at all these different things that we're looking for. All right, we could look at the shape. One or more arcs we're trying to assess. Might be confused with coronal rays, an edge. So an arc is a line of aurora. So they're sometimes curved. These are all images of singular arcs. Are you able to see my field guide when I open that tab?
Yeah, I can see it.
Okay. Sometimes I don't know when I share screen if it's all showing. All right, so these are all single arcs. Even this thing. So if you, any Harry Potter fans in the class? Do these look like Dementors?
A little bit.
All right, or what you imagine Dementors look like, especially this one. Okay, or, you know, the Patronus or something like that. All right, that's our shape. One or more arcs. Here is coronal ray shape. Very different. Okay, very different. You see the differences? This has these kind of streaking effects. I might have a hard time deciding if this is an arc or coronal rays, right? Next one. Here is something with an edge, and you might confuse this for one or more arcs, but the edge, this is like what I was telling you about, where it just cuts off and you have this dark sky and there's no kind of fuzziness on both sides, right? Very sharp. So if you see an edge, you want to identify that. Like this, I would have a hard time with that one. Aurora everywhere, right? If you look at things like this and you see them kind of smeared all over the place, that's what we call aurora everywhere. Okay. Are there irregular blobs? Is it patchy? Okay, that's different than aurora everywhere because it's just sort of like kind of random. No aurora, clouds and stars. Pretty obvious, right? How do you tell the difference between a cloud and an aurora? Well, sometimes it's kind of hard to tell. This isn't moving, really. Or if it is, it's maybe drifting across. This is definitely an aurora right there. Okay, that line, clouds don't look like that. So when I was in Iceland last March, a couple of students and I were out looking for auroras, and I thought I saw one, and people were saying, no, that's a cloud. And I said, no, because it kind of looks like a snake in the sky. So it's easy to confuse clouds and auroras sometimes, but if you see this kind of snake-like feature, even if it's faint, that's an aurora. All right, you're not only looking at shape, you're looking at movement. So this is drift, how it's kind of, all of these are examples of drift. Slowly moving across the sky. I'm going through this kind of quickly because I want to get to actually showing you how you do this. Ripples, and I'm not sure how this is kind of translating. Other things, curls, waves, or counterflow, okay? Not drift, it looks like waves. Chocolate sauce, okay. I don't know why they call it that. It's kind of spinning. It's a little different than the waves or the counterflow idea. Psychedelic kaleidoscope, that's another name for it, weird. Okay, and the last thing, if you're, oh, there's a psychedelic kaleidoscope example. But the last thing is fuzziness, okay? So if it's kind of indistinct, depending on, you know, what's going on, you'll see edges and not. All right, that's the field guide, always available on that tab on the right if you need it. Okay, so what we've been looking at again is the about to get you kind of your feet wet. Now we're ready to get going. So I'm going over here to the classify tab, and fortunately for you, you don't have to jump right into classification. There is, you could just go jump in and go right to it and start assessing, or you could go over to this tutorial, right? And this will walk you through it step by step. If you are doing this, let's see, you want to click on the play button, okay? So that is playing for you frame by frame, and obviously there's not that much going on in this particular image, but what we have to do, of course, is assess the shape and then the movement, because we were just talking about those things. So the tutorial I recommend, and I won't walk through it together with you, but what I want you to do with the rest of the time that you have for physics today, which should be, you know, something like 15 minutes maybe, is to go through this tutorial, or if you don't, you know, have the patience for it, go right into the task and start to classify some aurora, okay? So that you've got at least, you know, 2 or 3 behind you. Do as many as you like to do today that we can talk about in class tomorrow. Challenges, things that you're confused about, you could take screenshots. Okay, and we'll also go over the problems from last week. So for the remainder of today, go to zooniverse.org, make yourself an account, takes 10 seconds, and then look for the Aurora Zoo and follow up on this. All right, anybody have questions? No? Okay, I will post a link to Zooniverse in Google Classroom for you as well. All right, take care, everybody.
Thank
Thank
you.
you.
Thanks for
Thank
coming
you.
today.
Question.
Yes.
So I already classified one Aurora.
Oh.
I'm trying to see if this thing is Aurora. I think it's Aurora everywhere, but can I share my screen with you?
I think you can. I'm
Oh,
trying
I
to
can't.
stop the